Next, we're asked about what happens to the circuit after the switch has been closed for a very long time. Remember, when we say a very long time here, what we mean is that essentially things have come to equilibrium. That is, the current is no longer changing. And since the voltage across the inductor is equal to L times di dt, if the current is no longer changing, then this is just equal to 0. So we have no voltage across the inductor right now. Still, there is a current flowing through it. We'll calculate that in just a minute because we know that the energy stored in an inductor can be expressed as 1/2 times the inductance times the current going through the inductor squared. So now we know the inductance, we just need to know the current going through the inductor. Not surprisingly, we'll get that by using Kirchhoff's voltage rule. And so we'll go around this loop again, starting just on below the battery, going around in the clockwise direction. So I get minus the voltage across the battery plus the current that's going through this outside leg here, I times R, the voltage across the resistor, plus the voltage across the inductor, which is 0. We know that is equal to 0. And so that we find out that the current here going through the inductor and also the current through the resistor is just going to be equal to the battery voltage divided by the resistance. So we can substitute that into our formula for the energy stored. We get the energy stored as 1/2 the inductance times the battery voltage divided by the resistance, that whole quantity squared. Go ahead and I'll put some numbers in here. The inductance is 53 microhenries, so times 10 to the minus 6. The battery voltage was 6 volts, and the resistance was 17 ohms. Square that, plug all the numbers in, and we get 3.3 microjoules.